This next video is going to introduce another type of coordinate that we're going to see frequently-ish in the course. They're a little bit more annoying to deal with, spherical coordinates. So you'll notice that there's a lot of Greek going on at the top of the screen here. So we have a P-looking thing that's called rho. Okay, so we pronounce that as rho, R-H-O, or like rho, yeah, okay. Theta we recognize, okay, so I'm not going to mention that. And then these last two things, I have a red kind of bar connecting them. It's called phi. Typically, I'm going to use this one for the notation. It's just a phi and a phi variant. So they're different things, or they're different symbols, but they mean the same thing, okay? Okay, so it's like phi, phi, pho, fum. Okay, there we go. If you are reading Kali at all, she actually interchanges the order of the coordinates. So when we're working on problems in class, it's likely that I'm going to use this set of notation, but if you're ever reading through the book, make sure to pay attention to Kali's change in notation, because she puts phi before theta. Okay, so great. What does this mean? Okay, well, first of all, we're working in 3 dimensions. Okay, so let's get a 3-dimensional sketch going on. Okay, so now let's describe what rho is first. Rho is going to be actually the one that you want to graph last, but we'll go through it. Okay, rho is the non-negative, so that means that it has to be greater. Let's try that again. Rho is going to be non-negative. Okay, so 0 or more. Distance from the 0 vector, origin, to our point, or to, and I'm going to use Q instead of P just so we don't get rho and P mixed up. Okay, so Q is our imaginary point that we haven't graphed yet. Okay. Theta actually is described the same way as theta from polar. So this is the angle from positive x-axis. And phi is going to be the angle from positive z-axis. Okay, and then with all this we have some restrictions. So theta certainly can be anything 0 to 2 pi. But then to hopefully have some uniqueness and we don't overlap, we are only going to allow phi to be within 0 to pi. Okay, so it only goes a halfway around, because theta will go the complete way around. Alright, so when we graph this thing, you can imagine that we're going to, rotate by theta, and then we're going to go up or go out by phi. Actually, I lie. We're going to then rotate. So we're kind of on this plane that would meet along this line, and then we're going to on this plane we're going to come down by phi, and then we should be saying that our point Q is right there, and then rho is going to be the distance from the origin to point Q. Okay, so generally when I do this, I rotate by theta, then come down by phi, and then extend out along that plane Q, or extend along that plane by rho to Q. Okay, and one thing just to bear in mind is that while Kali does switch the order of them, some people even switch the meanings. So just be careful that that like physicists, for example, they might take theta to be phi and phi to be theta, and it's just really wonky. So definitions are important as always, so make sure to pay attention to that. Okay, and then now I want you to pause the video again and tell me what you think the graphs of each of these would look like. Okay, well, the first one is saying that the distance we are from the zero vector, the origin, is constant. Okay, and that's constant in any direction. So what do you think you get? I'm not going to bother to draw it out, but I think you should end up getting a sphere of radius c. Okay, and this also assumes that c is non-negative. Okay, that c is positive, I should say. If c is 0, well, then you get a point. That's boring. And if it's negative, well, then you get something that blows up the world. Not really. I digress. Anyway, next one. This is saying you rotate from the positive x-axis by c, and you can have any length along there. Now, this is the interesting thing. So let's just maybe draw a little sketch. Okay. So here's a little sketch. Okay, and you rotate from the positive x-axis by theta, and now whereas we would have said if we were in cylindrical this would be a full plane, keep in mind that rho is defined as non-negative. So actually here we only get a half plane. So we come out and down, something like this, and so we only get this little thing here, and so we get a half plane. And the last one, we're saying that the angle from the z-axis is constant. So if we draw this out, so we come down by this angle c, and then it comes out and it meets it, and then it can rotate all the way around because I haven't restricted what theta is. And what do we get? We get a cone. Okay, and I'll also say, well, it'll be a cone unless c is pi by 2 or 0. Okay, those are boring cases. If it's pi by 2, you get a half plane. Okay. All right, so just a little bit about that. And now if we need to worry about conversions, most certainly, they're a little messy, I won't lie. The first one is fairly standard. That's kind of like the equation of a sphere that comes to mind, so we won't worry about that one. The other ones, all I can say is time, energy, practice, and memorization. So go for that. Okay, so if we want to convert this one into Cartesian, well, the first one is actually kind of easy. You square both sides, so let's do rho squared is equal to 4, and then this is x squared plus y squared plus z squared is equal to 4. Okay, converting that into Cartesian isn't that bad. Okay, but now this next one, this one's a little wonky. Okay, so if we start with this, okay, so this is in cylindrical, so then if I replace this with, so I would, multiply by r to both sides, so I get an r squared here, and this would be 6r cosine theta, so this is really x squared plus y squared is equal to 6x, and then, well, from here, what do I do? Well, it's in Cartesian, so let's put in the formulas. So I get rho squared, and I'm just going to do c for cosine squared, cosine squared, sine squared, or sine squared of phi, and actually I should probably include the angles just so we keep those straight. Cosine squared theta, sine squared phi, and then this side is 6, and then we have rho cosine of phi, or theta, and then sine of, I want to write it out, sine of phi. Okay? So then I can certainly divide by, oh, and I forgot, actually, let's redo this. I forgot about the y. So plus rho sine squared theta sine squared phi is equal to 6 cosine theta sine phi. Okay, so then everything has a sine phi in it and a rho, which I forgot here. Okay, so then I can take out a rho, and this was supposed to be squared. Yep, lots of errors in this one. That's okay, we're catching them. Okay, and then I can take out a cosine of theta. Nope, I can't. I was going to take out a sine of phi. Sine of phi, sine and sine. Okay, and then I can factor out, so there's still a phi, or a rho on the left-hand side. Cosine squared theta. Actually, I can factor out more. Factor out a rho sine phi, and then cosine squared theta plus sine squared theta is equal to 6 cosine theta, and we know cosine squared plus sine squared, same angle, is 1. So then we end up with, if we solve for rho, we get 6 cosine of theta over sine of phi. And I'll actually write it all out just so we can see it all. Okay, so a little more ugly, but still doable. Okay, and generally when you're working with spherical coordinates, things are going to get messy quickly, so try not to use them if you don't have to. All right, a few more comments on cylindrical on coordinate systems, and then we'll move on to the little bit of topology we're going to see.